Outline. Non-reversible reactions should be pretty straightforward, like when you add hydride or Grignard, etc. Those cannot turn around and leave. Okay. Or numeral 2, which is the rest of the handout pretty much. Reversible reactions. Two types that I classified. Simple. We're doing simple right now. You can add water to an aldehyde or ketone. If you simply just add water, you're going to get what's called a hydrate or a gymdiol. You can do that mechanism catalyzed by acid or base. What do we do it? We did it with base.
Yeah.
That means you have aqueous hydroxide. Hydroxide is added, then you pick up a proton. If you do it with acid, what's going to be the first step? Protonated carbonyl. Carbonyl chemistry with an acid catalyst. The first thing you always do is what? Protonated carbonyl. Simple as that. After you protonate carbonyl, then what would you add to the carbonyl?
Water.
Water, not hydroxide, water. Then you'd have to lose a proton over there. What would take the proton?
Water.
Water or whatever gave it up to begin with, the acid anion, like Cl- or something, or sulfate minus. Okay? Very straightforward. Most hydrates are not stable. You can't make most of them. Okay? This is the favored form. So then you just see them in unique cases, or maybe mechanisms. Okay? Some you can isolate. Chloral hydrate, this hydrate is stable. And if you go run an IR of it, you'll see two OH groups, and you won't see a carbonyl. Okay? Why is it stable with the 3 chlorines? First off, what is the, if you lose water, what do you go back to? You go back to the aldehyde, minus water. Okay? This way is plus water. Okay? You gotta see how you go back there. Essentially, to go back, you would kick off one of the hydroxides and make double bond, and then hydroxide would take the H. Okay? Anytime you make a pi bond kick off a leaving group, that's easy to do, typically. Okay? This is going to go backwards. Well, in this case, it will not. Why is this a favored form with these 3 chlorines here? Well, the 3 chlorines are very withdrawing. They're greedy. Greedy little suckers. Okay? Well, what does that matter? What's the hybridization of the carbon here? sp3. What is it here? sp2. See, there's a hybridization difference there. Would all those greedy, they're not bonded to that carbon, but they're next door. Okay? And these chlorines are essentially pulling this way. And which compound are those chlorines going to be able to get more electrons? The sp3 carbon. Why?
Because it holds on to its electrons less tightly, but the orbital's not supposed to.
Right. And sp3 carbon, the orbitals, this orbital here is not held as tight by that carbon. So all these chlorines can pull. And they're like, hey, I like to pull. Hey, I like this situation. I get what I want. Over here, the sp2 carbon holds its electrons tighter. The chlorines can't pull as much. They don't like that as much. So once you hydrate, the chlorines are like, ooh, I like this. The molecule just likes it better. The electrons get to be pulled to where they want to go. Like electricity going to ground. Okay? It's caused a difference in hybridization. If this is just CH3, that's actually the favored form because the carbonyl is actually a very strong bond. But this dipole here apparently overrides it. Chloral hydrate is also known as, what is that known as? Or what is it? It's a sedative. Yeah, very good. People used to give like drops in their somebody's drink, call it like a Fin Mickey or something, or knockout drops. But like gangster movies back in the 1930s and 40s. Slip them up.
Oh yeah.
Yes, yeah. But it's that. It's a hypnotic. Of course, this can this go back to the aldehyde? Can that go to the aldehyde?
Yeah.
Sure. If you don't think so, look at Roman numeral 2. What does it say?
Reversible.
Yeah, reversible. All these are reversible. Okay. Now, at equilibrium, this is favored, but that doesn't mean it can't go back. In the body, it does. And this is basically, if this were H's, what would that be? This is acetaldehyde. This is what ethanol is converted to when you drink it, and this is what causes you to be drunk. Okay? Ethanol, which is that, if you oxidize it, you get the aldehyde. It can be oxidized further. This is, but with these chlorines here, it makes it particularly potent. Those chlorines probably help it get into certain places in the brain, it's more lipophilic. And it's like giving you a super high dose of alcohol, essentially, in the already oxidized form. Yeah.
So if people are just trying to get drunk, why don't they just drink back?
You probably die if you're drunk. All you need is a couple of drops of that. All right? It's too potent. All right? I'm giving you just a little bit of free information here, make it all relevant, okay? Where have we seen hydrates before? I forgot that this was here. Remember oxidation of aldehydes to the acids? It actually goes through the hydrate. That's where the other oxygen comes from. Okay, form the hydrate. Now this is not the preferred form. Like I said, this gets oxidized on and it makes this go this way. Your equilibrium adjusts. Hydrates are often sort of just seen in mechanisms, or occasionally you'll see them in biochem. That's a hydrate. Okay, another simple addition product is reaction with HCN. And this gives what's called a cyanohydrin. Cyanohydrins are stable. You can isolate cyanohydrins. Okay? You can do this different ways. ACN is a weak acid, so I'm hesitant to protonate the carbonyl. But you could, some books may show it, but it is ionic enough to have the cyanide ion. I'm going to do it without this being a strong acid. Add the carbonyl, electrons up. Of course, that gives boom, 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 electrons up. O minus, Cn. That's just a simple nucleophilic addition. And then how do we get the product? Of course, this then takes the H, and there you go. Okay? Some books may show protonated carbonyl first. It depends on how strong of an acid you consider that. Usually you don't want to protonate something unless you have a strong acid. ACN it is called hydrocyanic acid sometimes. It's borderline acid.
Would sulfuric acid as a catalyst help that reaction?
You could put in a little sulfuric and it would protonate it, and then, yeah, you could envision how that might catalyze the reaction. That would definitely protonate it. Then the cyanide could add. Now, actually, we'll look at this down below, I think, a little bit. Okay, so that's a cyanohydrin. You need to know all these functional groups, okay? There are additional functional groups. You may remember halohydrins, okay? The halohydrin, the halide and the OH were not on the same carbon. If you go back and look at your halohydrins, you make them alkenes in organic form. Cyanohydrin, the C and the OH are on the same carbon. At least the most common ones, okay? Halohydrin. I don't know why I put the X on the same carbon. Usually your halohydrins, remember in organic 1, the OH and the halide were vicinal. Right? There's a 50% chance you'll see a halohydrin on the final exam. So I'd probably go and look that up. There's a 50% chance you'll see anything we've ever talked about on the final exam. Okay, so cyanohydrin, just a simple addition. You can't isolate them. Can you be reversed? Can a cyanohydrin go back to the allied ketone plus HCN? Sure, we're in Roman numeral 2. Okay? You need to be able to show, what if this reversed? What would the allied ketone look like? There you go. It's basically this reforms carbonyl and kicks off the cyano. And you lose the proton. So you got to sit down and see this. You can't just look at this and think, next time I see it, I'm going to be able to do it. You got to see how this gets back to the carbonyl. Okay? You know what? With acid derivatives, all acid derivatives can be hydrolyzed back to the carboxylic acid. Well, all aldehyde ketone derivatives can be hydrolyzed or converted back to the aldehyde or ketone. Okay? So if this would give this, but if it reversed, it would give this plus what? It's in the box.
HCN.
HCN. Thank you, Mike.
Yep.
What do we know about HCN?
It doesn't taste good.
It's toxic. It's deadly toxic, okay? It smells like almonds. If you ever smell almonds in the lab, I would probably evacuate. HCN, deadly toxic. What do you think about the toxicity of these then? Would you like to ingest a lot of this?
No, because you have a lot of enzymes.
Well, this with heat or time or biological enzymes can reverse. Any of these are reversible under certain conditions. You ingest a lot of this, you're going to be producing HCN in your body and it's going to be not good. Actually, about 10 years ago now, maybe longer, over in Africa, a lot of cattle were dropping dead. And they couldn't figure out why, what was going on. Turns out some of the hay that they were eating at the time had been, there was some type of microbes growing in the hay, and the microbes were creating a cyanohydrin. And when the cows ate the hay, the cyanohydrin converted back to this plus HCN, and the HCN killed the cows. They finally figured out what was going on. Okay?
Dr. Stephen, what drives the reformation of the double bond to the O?
Anytime you make the pipeline kick off the leaving group, decent to do. Cyano is a decent leaving group, okay? Have you ever seen CNB minus? Yeah, see, CN has a good amount of stability. Sodium cyanide. ACN is a fairly good acid, a strong acid. Because CN minus is stable enough to be minus. As we said before, we'll even see carbons leave. Look back when we first introduced this. I even showed cyano on that page. If you've ever seen it be minus, you can probably leave here in this fast step, reforming double bond. Okay. But you're not going to kick off just a plain nothing, or like a plain H, even though we have seen H minus. Okay. But this is a case, and this is just equilibrium. Okay. These things can reverse. Okay, let's look at making these another way. If we're going to make these next week in lab, would you like to use HCN gas? No, I would not want you guys to handle HCN gas. Okay? You guys, unfortunately, have a tough time just putting caps back on solid reagents. Okay? We can't have a student coming in using HCN gas and just leaving it open and letting it just go everywhere. Okay? Because HCN gas will chase you around the lab and around the building. A solid will just sit there. Okay? So, what do we need to make a cyanohydrin? We need cyanide and an H+ source. Do those have to come from HCN, or could they come from maybe this setup? Will that supply cyanide, won't it? And will that supply proton? What is this? I don't think we ever used this. This is bisulfate. See, H2SO4 is diprotic, right? But HSO4, even though it's an anion, still has one acidic H. And you just put a potassium here, or sodium. Okay? See, sodium bisulfate has one acidic H remaining. Why use it compared to this? H2SO4 is a liquid. You spill it, you're going to have a big mess. Is this a liquid or solid?
Solid.
It's a salt, okay? It's a solid. You spill this, you just sweep it up with a little broom. So that's a solid acid. Okay? It's just a practical convenience. So, what do we have? Instead of a toxic gas, we have actually two solids. Which would you rather use?
Solid.
Two solids, easier to weigh out. You spill it, we just sweep it up. Okay? Question?
Yes, isn't like the equilibrium constant of the second H for that like way lower than the first one?
It is. It's not probably considered a strong acid, but it's acidic enough. Because, just like up there, it may not protonate the carbonyl, but once it adds, the O- is going to take the H. So it depends on when it gets protonated. That's why I didn't protonate the carbonyl up there. Typically, you only protonate things with strong acids. Okay? And you have about 7 strong acids that you learned in Gen Chem. You don't want to protonate something with water. Okay? Water is not an acid. I'm saying this because of the mechanisms. There are lots of positive charges under basic conditions. Just not going to have something protonated under basic conditions, or even under neutral conditions. Okay, so practical. We just see just a new acid there. That's just a solid acid. What if we took this and heated it with aqueous water? Aqueous acid. Aqueous acid. What might we get? We'll final exam time, huh? We'll review. What would happen? What kind of chemistry could take place?
Protonate the nitrile.
You protonate something, yeah. This implies strong acid. Protonate the nitrile or the OH. You can protonate this can ionize, you get cation. What can attack cations? Water, and you would get the same product back. See, that's not really going to lead to anything.
Diamondization.
If this was HCl, you can envision protonating and ionizing and chlorine added here. This typically can bond, when you see this H3O+, that implies that the anion is not nucleophilic. Okay? If they wanted you to show a BR on the product, they would have showed HBr. So this implies that your anion is not nucleophilic. The only thing are you doing your ring chemistry with just aqueous acid? There's nothing you could do. The electrophile would be H+. I mean, the product here would be, are you going to eliminate the OH to make an alkene? No, we need another carbon to make an alkene. You're not going to make an alkene to that carbon, it would then have 5 bonds. What you're going to get here is carboxylic acid. You're just going to hydrolyze the nitrile. Okay? Intermediate would be the amide. But then you could say, well, the amide could get further hydrolyzed. Okay? Basically what I'm showing here is that you can do chemistry with your product here. We know chemistry of nitriles. Okay? Now if there was another carbon here or something, maybe we can eliminate, put in a double bond by an E1 elimination. So that's the idea of, hey, what type of chemistry could happen? And at this point, we know more and more chemistry. Okay. Toxicity of cyanogenic glycosides. Hey, there's a good term. Where do you find cyanogenic glycosides?
And peach pits.
Very good. I didn't think anybody would, yeah. How you know that, T? Huh? Oh, man. Yeah, have you ever heard of don't eat the pit of a peach or something? Yeah, it contains cyanogenic glycosides. Glycoside is basically a fancy term for like a sugar or carbohydrate. It's a carbohydrate that's in the form of a cyanohydrin. Okay, I think this is in the white handout, the one you printed. There's lots of applications of this aldehyde ketone chemistry. Again, when you get to biochemistry, you're going to see. Okay. It's on this page here. Make it a little smaller. I'll sometimes refer to this, sometimes we'll just have to move on, and I want you to look at this on your own, ask questions, etc. This is a cytogenic glycoside. Okay? Usually these sugars have lots of OH groups. Here, this OH is now sort of bonded to this carbon. Okay? What functional group is this right here? Now that over there is an acetal. We'll learn that soon. What is that?
Ether nitride.
Cyanohydrin. Not exactly. This is not an OH. It's sort of an ether where the cyanohydrin, the oxygen, is an ether. Okay? Some people may call this a cyanohydrin. Basically, instead of an H, it's got an R group. Okay? First off, acetal can be hydrolyzed. We'll see that. And when it's hydrolyzed, you get the cyanohydrin, the true cyanohydrin. But then the cyanohydrin can convert back to your aldehyde ketone plus HCN. Okay? Again, we'll see acetals in a little bit. Basically, you have two functional groups here. Both of them can be broken down and reversed. So you might look back at this after we cover acetals. But this is like prevalent in like the pit of the peach. Things like this were what the microbes started creating in the hay over in Africa. Okay? And then this broke down and killed the cows. Okay, so the two simple addition products are your hydrates and your cyanohydrates. We'll now move to not so simple additions. These are going to be additions with loss of water in the mechanism to form the product. And what we'll see is the carbonyl oxygen of the starting material will eventually be lost as water. Where in the cyanohydrin it was not lost, it just became protonated and it was still there. Okay? So, in this here, if you star that oxygen is now over here with water. And there will be numerous reactions like this. The first reaction is reacting your aldehyde or ketone with an alcohol and an acid catalyst. And you do need two equivalents of the alcohol if you want to balance the equation. Okay. Now at this point, mechanistically, I would expect you to pretty much already be able to do this. Let's do it together and see how we get what's called an acetal. Do you need to know these functional groups? Acetal, if these alphas were H's, what would it be called? Or a hydrate. Yeah. Acetal is where your two H's of your hydrate are R groups. Okay? It's basically a carbon with two ORs. You might be prone to call this a diether. It kind of is, but it's got a specific name. The two oxygens are on the same carbon. Okay, you got to know these functional groups. All right, what's the first step you want to do here?
Protonated carbonyl.
Protonated carbonyl. Very good. This implies strong acid. Okay, your favorite strong acid. What is that going to give? Well, it's going to give protonated carbonyl. That makes the carbonyl more electrophilic. Nucleophiles are more prone to adding because that electron the oxygen won't seize electrons. What's the nucleophile?
Oxygen.
Ethanol. Boom. We get boom, 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 electrons up. We get now an OH there and O ethyl H. Now, I'm not going to go neutral, but if I just took the H back, you would have an OR and an OH. And that would look like a simple addition product. But it doesn't stop here when you have an alcohol. I'll come back to that sort of halfway product. Instead, that oxygen there is going to leave as water. What we said, right? What do you want to do next?
H transfer.
H plus transfer. Let's put it on that oxygen. I mean, why should this oxygen have the acidic proton? That oxygen is just as basic. I would give that. H plus transfer. Now what you want to do?
Second ethanol attacks. Water leaves.
Make a double bond and kick off the wall.
Yes, anytime you make a pi bond, kick off the leaving group, it's going to be easy to do. Anytime you make a pi bond, you use a lone pair. What does that give? I do this methyl up, double bond, the oxygen now positive charge with an ethyl, plus what? Plus water. There's our water. And the carbonyl oxygen got kicked off. Okay? But see, this thing cannot go neutral. It doesn't have an H to lose. So what happens here, another equivalent of ethanol, that's an upside down carbonyl. And if that was an H, it would be a protonated carbonyl with a positive charge. But instead of an H, it's an ethyl, which can't be removed. So nucleophiles will add here, just like a carbonyl. And we kick these here. I'm going to come this way a little bit. That's going to give boom, boom, boom. O, ethyl. That's now a neutral oxygen. We've got the methyl there, and then we have an OH. So that's where the nucleophile came in, electrons went to oxygen, yep? Now what do we need to do to get the final product? Something takes the H. Whatever gave up the H. What's here? Your favorite acid. Maybe it's an HSO4 minus here because you use sulfuric acid. This can take the H, leave it behind, you get your acetal. Or you can use water. You can always use water because then you'll just make H3O plus, and that's how sulfuric acid exists. Okay? Now this is a true equilibrium reaction again. Can the acetal react with water and go back to this? Yes, we're under Roman numeral 2. Reversible reaction. Okay? And if you see an acetal, you need to be able to say, well, what would it go back to? Okay? How do you drive this to the acetal? A large amount of alcohol. You take your aldehyde ketone, just a lot of alcohol like a solvent, and add in a drop of acid, heat it up. And all that alcohol will make it go to the right. Okay? Or maybe you can remove water as it's formed. Can this reverse? What's the reverse mechanism? You should sit down and do it on your own. The reverse mechanism is already up here. What would you do first with the acetal? First off, you would have the acid catalyst going the other way. protonate something, protonate one of the oxygens. And if you did, could you then move these in and kick off the oxygen?
Yeah.
And if you did that, instead of ethanol adding, could water add here?
Yes.
Then you would get the water added. And after water added, could you move the proton to the ethyl? Sure. And after you did that, could you do these electrons to kick off the ethanol? Sure. And then you take the H from that. This can go both ways. How would you, if you had an acetal, how would you convert it back to the aldehyde ketone? Lots of water. Or you remove the alcohol in its form. It might be a little difficult. Or maybe not. Okay. So that's an acetal. Can you recognize acetals? Well, go back over here. This is cyanoglycogen. Why do I call that an acetal? Well, that's a carbon there, right? What's it bonded to?
Oxygen R groups.
An OR and an OR. That's a carbon with two OR groups. And when it's hydrolyzed, what does this carbon become? Good. It becomes carbonyl, and the two oxygens get kicked off as your alcohol is getting kicked off. That would get kicked off. But when that oxygen gets kicked off, what does it become? What I showed there. That's like one of your ethanols being kicked off in the reverse of the acetal formation. Okay? I mean, all this takes is like a little proton, and then this oxygen going, boom, there you go, I just kicked off the OH. So a little acid catalyst, and that thing will just decompose back to your carbonyl compound. Okay? Now, in practice, you do have to drive the equilibrium when you make acetal. Okay? Let me ask you this, back over here. In practice, in lab, what do you think about removing the water as it's formed in this exact reaction? Is that feasible?
Probably use like cool glassware to do it.
What is the,
Yes, you can. Usually, can you distill the water out? What's the boiling point of water? 100. Okay. Can you do this and distill the water out as it's formed?
yeah, no, I know the first. Yeah. Ethanol's got a lower boil than that one.
Yes. Boiling point of ethanol is about 78. Okay? So you can't do this at 100 degrees, or you'll be, your ethanol won't let you go to 100 degrees until it's boiled off. Then you can go to 100. Okay? So you have practical, and boiling the water off is one of the most common ways to do it. Yes, there is fancy glasswares. Yes, you could put some type of drying agent in here, like molecular sieves, or even like anhydrous sodium sulfate might help. But boiling it out, the original practical way is really not feasible there. That's why the next modification was sort of developed. Making acetals using diols. You need two equivalents of your alcohol. What you need is two OH groups. The two OH groups can be within the same molecule, and that would be called a diol. If you use a diol, you'll get a cyclic acetal. And in this case, I'm using para-toluene sulfonic acid as my acid catalyst. Oh, I forgot to show you something. You remember the acetal we had there? I don't know how many carbons it was. But at one point we had like an OH, and then we had an OR. Is that right, T?
Yeah.
And then, see, I've transferred the H here. If we go completely neutral, we can show this. What is that? Is that an acetal? An acetal has a carbon with two ORs. That's an OR, but that's an OH. Is it a hydrate?
No.
No, a hydrate is two OHs. It's not an acetal, it's a half acetal. Y'all heard of half acetals? I think Larry's heard of that. Half acetal. It's officially called a hemiacetal. Hemi stands. I call it half acetal. Okay, how can we make this here? You should be able to do this on your own. Okay? Please do it on your own and let me know if you have any questions. Basically, at one point in the mechanism, we had something like this. And the alcohol added. Look back at your mechanism. Didn't we have something like this? Okay. And then the alcohol added here. And we got to something that looked like something like that. No, we don't need to do this. Is with ethanol. I've already erased it. I don't want to redo it. You got it in your notes. At some point in the mechanism, when we brought in this second equivalent of the ethanol, it was a totally separate molecule. In this case, the second OH is going to already be there, hanging off the end. You just bring it in, you're going to make a ring. Okay? We'll do that on your own and let me know if you have any questions. Acetals is aldehyde ketone protecting groups. What are acetals good for? Oh, this is one thing they're good for. Acetals don't tend to be final products because they're just too unstable. They'll revert back to the aldehyde or ketone. Occasionally, though, you do see them. Some are more stable than others. And actually, on the very front warm-up page, we have triamcinolone. The difference here, these two OHs. Now we have this structure, triamcinolone acetonide. What functional group do we have right here? Acetal. Yeah. See, this drug actually has an acetal. Please answer some of those questions there. Okay? Acetals can be used as protecting groups. What do we mean by protecting groups? Look at this reaction here. If you take this beta-keto ester, see that's an ester, it's an alpha carbon, it's a beta carbon, and it's a ketone. It's called a beta-keto ester. You'll see these all over the place in biochem. React it with LAH. You're trying to just reduce the ester by additional elimination and addition again to give this product here. You're not going to get that product. Because the hydride will also react over here by just addition. And this is actually more electrophilic because an oxygen donates more than the methyl. Question, gotcha.
So even if you use like a weaker agent like diol H, it's still useful.
Well, the last thing I said, this is actually more electrophilic. So that's actually the one that's going to be attacked first. You understand why that's more electrophilic? This donates by induction, which is mild. That donates by resonance. It's a stronger donation. Aldehyde ketones are more reactive than like esters and amides. So, we've got this more reactive functional group, if you just wanted to do chemistry here. But what we can do is we can make an acetal of that. Show the acetal that you get by reacting this with this. Since this is more reactive, all this does react here, and you can make an acetal. So show that acetal. Okay, acetal would be boom, 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 boom.
Isn't there one more carbon?
Yeah, there we go.
Yes.
That's why I was.
In my mind, I was drawing another carbon. Rookie mistake. How about that there? Yeah, the two alcohols get on the carbon instead of the carbonyl, right? They're joined. You got to see, okay? We're doing chemistry here that if you don't sit down and critically look at what's going on, you can't just memorize, okay? Because there's going to be... There it is. It's the same old thing we did before. Make the acetal. It will react here selectively. This can be isolated. At this point, you then throw in your hydride reagent. Okay? This is no longer electrophilic. Nucleophiles will not add here. This is only reactive under acidic conditions. It's basically back to an ether. Remember ethers. Ethers are unreactive under basic conditions, such as epoxides. But this is not ring strained. It's not going to, okay? This will now do your boom, boom. It'll add twice, and you will get the boom, boom, boom. 1, 2, 3. Okay. Boom, boom. And this will become what? Okay. This is where the hydride adds twice. What's the intermediate here? Aldehyde. When the H kicks off the O-methyl, but then another H comes in. Okay? Get this here. Now how can we convert this to A? Well, that's an acetal. What do we want to do? We want to unmask it or deprotect it. See, this is protected. Deprotect it using H3O+, water and acid. And you'll go back, you'll hydrolyze your acetal back to the aldehyde ketone. That's the reverse of making an acetal. Adding lots of water and acid. Okay? All three of these steps you need to sit down and do mechanism. I can't stand up here and do those three mechanisms for you because that's going to be meaningless. You've got to sit down and do it yourself, making mistakes. But it's all very straightforward chemistry. Okay guys, when we come back we're going to be hitting the ground running hard. Lots of aldehyde ketone chemistry. Please have a happy, safe, enjoyable break. See some of you in lab this afternoon.